Imagine a world where the possibilities are endless, where everyone can participate and everyone can prosper. A world where how we live, how we learn, how we work, and how we play are all transforming. This is the world we live in now. There are already 30 billion connected devices and 200 million plus connected devices each new day. It's a world where every part of our lives is advancing faster than ever before. With 1 trillion connections by 2030, half of the world's population is on the web, where cities are becoming the centers of learning, culture, careers, and rising economies that enhance our lives. At the speed of digital, innovation is transforming our planet. From smart factories to space exploration, from virtual medicine to energy alternatives and sustainable farming, from cutting-edge medical science to the world's most advanced semiconductors, we are redefining technology to make our world a better place. Led by networked intelligence, social media, mobility, AI, IoT, and big data, we have entered the 4th industrial revolution, and it is disrupting every industry, every country, and every life for the better. At SEMI, we serve this incredible ecosystem that helps make the digital world possible. That's why our new story is so much bigger, because SEMI is more. Today, we're extending our reach from semiconductor design to equipment, materials, devices, and applications. We're driving value in workforce development, expos, standards, and R&D funded programs. We're providing insights and exploring new opportunities with thought leadership. We're inspiring innovation and industry engagement through our technology communities and partnerships. We hold the big conversations that drive growth, influence public policy, and help make technologies safer. And together, we fuel endless possibility. SEMI. Together, we are reshaping tomorrow.
Good morning, everyone, and welcome to the second day of the Connecting Heterogeneous Systems Summit 2021. My name is Marek Isela, Senior Coordinator for Advocacy at SEMI Europe. In today's first session, we will take a closer look at the latest advances in smart manufacturing and Industry 4.0 enabled by the MADEin4 project. As an EU-funded collaboration, the MADEin4 project is a consortium of 47 partners from 10 different countries, with the objective to develop the next generation of metrology tools, machine learning methods, and applications for Industry 4.0 high-volume manufacturing in the semiconductor and automotive industry. But more on that from our today's speaker, Mr. Yoav Hirsch from Tower Semiconductor. Yoav, the floor is yours.
Thank you, Marek. And thank you for inviting me as a speaker to this event. I will try to shine some light onto the latest developments and innovation within Tower are taking place in the semiconductor industry. I'll start with a few slides on Tower Semiconductor. Tower was founded in acquisition of National Semiconductor's 150mm fab in Israel and became public in 1994 at NASDAQ. In 2000, it became public also in the Tel Aviv Stock Exchange. Fab 200mm was established in 2004. In 2008, Tower merged with Jazz Semiconductor. It's a US fab. It was merged with the stock exchange. But the biggest jump was the joint venture with Panasonic fabs in Japan with the formation of TPSCo. So Tower is 51%, I think, of TPSCo, and Panasonic is 49%. This joint venture enabled Tower to offer 300mm fab services with technology node down to 65 nanometer. Overall capacity of Tower is about 800,000 wafers a year, 8-inch equivalent. But the latest expansion is with the joint venture we done with the ST Agret in Italy, also expecting to expand our capacity in 300 millimeters. Now, Tower's position globally is now at three continents, Asia, Europe, and the US. The COVID-19 was with very little influence to production. After the early shock was over, we are now in a surge of production in all our fabs. Of course, the latest announcement is, of course, the expansion program with the ST Italy, and we now have so now we have a footprint in Europe as well. Towers successfully shows a constant growth. Regardless of the known ups and downs in this industry, it is very tough market. And as we all know, the current trend for production of the semiconductors in the next few years at least looks like a sharp high. In this file, you can see the worldwide manufacturing capability of Tower, unlike what many people would probably think on the 150 millimeter Fab 1. Our Fab 1 is full, and not just even full, it's overloaded, even some with new customers. So for those who think that all technologies are past, they are not past, they're here with us. One could also notice the Tower's specialties in the analog market. The digital is mainly occupied by the big names, Samsung, Intel, TSMC, UMC, SMIC. Tower fabs and technology offering is mainly around the power, automotive, image sensor, and so on. Large portion of the analog market is turning nowadays into the automotive rapid growing market. ICA, the International Council of Archive Publication last year, I think it was it's December 2019 to be exact, forecasted by 2030 there will be an additional 300,000 metric tons of copper in only for wire harnesses each year, and this number is growing. This is due to vehicle electrification technologies, you know, the hybrid batteries, EV, 48 volts, start-stop systems, etc. Tower has a very strong position at that market as part of its analog solutions. Now, you can see here in this slide the vertical technology node versus analog technologies, and Tower production capabilities shows across the production technology metrics for capability and existence, also in the automotive. From power through logic to CMOS image sensors and non-imaging sensor automotive parts are everywhere. Almost every electronics existing today in the automotive industry is also being serviced by Tower manufacturing capability. It starts from ADAS, LiDAR, magnetic sensors, power electronics, spot-based LiDAR, SWIR images based on germanium diodes, etc. The global automotive electronic market size counted about $256 billion only in 2020. And I'm talking about electronics for the automotive. And expecting the prediction is that by about 2030, only electronics for automotive will be in around $640 billion. So this was all about the background of Tower. Before I show some of the latest innovations in the analog semiconductors, or specifically on the image sensor, I'd like to touch a little on the challenges of machine learning. Now, as we all know, in Industry 4, it's all about information. Machine learning, artificial intelligence, all these buzzwords exist in almost every presentation you're going to see. The bottom line of Industry 4 is that is to enable machine communication socially. The challenge of all this for us as the manufacturer is not just to make the sensors smarter, but we need to transfer those smart sensing quicker and much larger numbers of data points. The idea behind the artificial intelligence and machine learning is the ability to transform data into useful information. And I'd like to emphasize on this. We've got tons of data, but how much of this becomes useful information? Example of a good idea is, for example, to make a smart decision right in the heart of the sensor. Transfer only the useful information outside, rather than just, pushing out a raw image. Now, three major market trends shine a direct light on the challenges we've just showed in the previous slide. The mobile market continue to grow, and we can see it in towers. 36% of the corporate revenue is only from the mobile market. Power IC and image sensors are growing compared to discrete and non-imaging sensor. There's also a growing movement to make the sensor smarter, embedding AI and machine learning right in the heart of the sensor, as I mentioned earlier. Now, mainly the automotive market dictates a whole new standard for quality and striving for zero defect. Unlike the mobile market, in the automotive market, the product must prove to live longer, as we know. Price of quality is rapidly growing as the product continues to move up the chain of integration. We will all agree that scrapping a wafer is much cheaper than scrapping a complete system due to a faulty chip. Now, this implies a rigorous methodology of attention to quality from design stage to wafer manufacturing and rapid analysis of faults to feedback any changes back to the design. Every aspect of the manufacturing is now under scrutiny. Now, this can be shown in these slides that depicts the various standards system methodologies exist in our manufacturing stages. Establishing of quality methodology in every aspect of the semiconductor manufacture exists for many years. Now, in recent years, there are activities to also enhance the CAD system of the designer with the data that propagates back from the manufacturer. Now, this is also a part of Tower's activity in the MADEin4 consortium. So, now I'd like to say a few words about the latest innovation of image sensors as we see them in Tower, and Tower has a very strong foothold in this industry. I would like to focus on three major fields of the CMOS image sensor that are prominent in this field. The first one is the global shutter fast image sensor. The second one is the low-cost special images, and the last one is the 3D imaging using time of flight. Now, the global shutter sensors is mainly characterized by very fast data images, small pixel, low noise, and large formats, as shown in this trend. Now, with our stitching capability, images can be larger than a mask field, and die size can reach up to 1 die per wafer. So imagine that if you have a wafer of 200 millimeter, you can have a chip of that kind of size. Or if we have a 300 millimeter wafer, we could also have a 1 die per wafer on that size. Now, most of the new devices are now manufactured in 300 millimeter wafers, now mainly for the yield reason, value for money. Now, when we say a global shutter, we immediately understand that after we stop the shutter, we need to keep some charge inside the pixel. Now, this slide goes a little bit deeper into the semiconductor exact device. We need to keep some charge inside the pixel until it's being piped out. So you take a picture and you open the shutter and then you close the shutter, and now all the data must be stored in the pixel. Now, latest innovation of the global shutter pixel is the capability of storing charge inside the pixel in a memory node, what's shown here as MN. Now, this memory node must be protected from the incoming light. Otherwise, photons will generate parasitic electrons inside the memory node and corrupt the data. In this development, we have applied a tungsten shield above the memory node, preventing light from penetrating into the memory node. On the right image of this slide, you can see a ray tracing simulation depicting the protection of the memory node from incoming light. So you can see the light as red and yellow, and on the right side you can see the blue. You can see dark blue is the tungsten shield and the memory node below it, and it's like it's protected from light. And as this mentioned earlier, we want to make the sensor smarter. So the challenge is both to decrease the pixel size, but also increase the number of transistors in a pixel. Now, this also was a part of MADEin4 development that we are proud to be a part of it. In this slide, I just want to emphasize the importance of a global shutter. You can see on the upper picture, you can see a picture of a rotor, a picture of a helicopter, that this image was taken by a global shutter, while the bottom one was taken from a rolling shutter. And if you look at the rotors of the helicopters, one can immediately see and understand why we need a global shutter to take fast images and not getting a smear data. Sorry. Take this up. Now, to summarize what was said in the global shutter, let me see, I'll reduce this noise. Sorry for that. I understand that you can barely hear me right now, or you can hear me well. Okay. So to summarize, right? So to summarize what was said so far, the global shutter technology is mostly fit in industrial and machine vision. It is so needed for the machine learning and in AI. And it is characterized by the need for very low current, high Now let's move to another exciting technology. Market growth is shown for all image sensor market, from medical to high-end photography and industrial machine vision. But the main upside of the market is shown with the need for 3D imaging, LiDARs, augmented reality, virtual reality, etc. In this technology, we need an ultra-fast responding sensor. And you can see how the market for this new emerging high growth market is sharply high. Now, I'm touching base a little bit on time-of-flight sensing. This is at the pinnacle of today's CMOS image sensors R&D, is the 3D imaging. We all heard about the Microsoft Kinect with its gesture control technology, but how does it work? The basic technology is a sensor that is fast enough to measure the time it takes for a beam of light to travel back and forth. But the mind-blowing fact is that a sensor is sensitive enough to distinguish the distance from our nose, to our ear. And it's really exciting. And there are mainly two groups of the time-of-flight technology. There is the indirect time-of-flight and the direct time-of-flight. I'm not going to go deeply into this because it will take me hours to talk about that. Now, in this slide, I want to demonstrate an exciting way of heterogeneous system architecture, where we use a stacked bonding in a pixel level. In this technology, we bond two wafers from different technologies, and after grinding the backside, we get one single wafer after we bond the two of them. But the final wafer we get is with two nodes embedded in it, two technology nodes. In this example, I show what we call the SWIR sensor based on germanium diodes bonded to a logic wafer. It's very difficult to see. Only I did mark here a little bit where is the GE photodiode, and you can see here the line, the blue line that shows where we connect the two wafers together. So we have copper and we have metals on the bottom and metal, some metal layers above. So you can see here on the left which one is the logic and which one is the sensor. So the ROIC logic sensor is manufactured in our 0.13 micron technology, while the germanium diode is manufactured with 0.18 technology. So what's the big deal? Well, what's the big deal in I don't know, in bonding these two wafers together? Now, the great thing about it is that we could engineer very carefully the SWIR pixel without worrying about the thermal budget effect on the logic circuit. For those who knows in the semiconductor, you cannot put the wafer too much time into a furnace, into an oven. You have a limitation on the temperature you can apply to a wafer. It changes the characteristic of the CMOS. So when we do one wafer in one technology, we don't have to worry about what we do for the other wafer. Now another thing is the fingerprint recognition, which we all know in a cell phone. Now the fingerprint recognition in cell phone was there in the beginning. And then came the facial recognition with better functionality enabled by more and more advanced cameras. All the phones, everything was with facial recognition. We didn't have to worry about where to put the finger and losing it. So everybody was happy, and everybody saw the light at the end of the rainbow. That's it, we're there. And then came the COVID-19. Now with the COVID-19, with the face masks on it, it was a blown to the face of face recognition. And fingerprint is back into the game. Most cell phones now are racing into adding back the fingerprint, and most of the fingerprint sensors are capacitive ones with a lens. Now they are very thick, but now as the phone gets thinner and thinner, you got less space for the fingerprint. So what they now want to do is they want to get rid of the lens, and that what evolves from that is that the sensor must be in the size of our finger. So the sensor becomes much larger, what is known as one-to-one fingerprint sensor. Very good news for the semiconductor manufacturers. Okay. Now, let us talk a little bit on displays. As we all know, we know about the LEDs, OLED TVs, but for the analog manufacturers like Tower, today's displays are being targeted mainly for the smart glass, as I said before, augmented reality, virtual reality imaging, aiming to reduce the pixel size, increase the contrast, but we need to keep the low power for all the handled devices. Now, almost all the big names we can think of in the tech industry see micro OLED as the next big thing. Micro OLED has a higher brightness and is more stable than OLED because of its inorganic nature. In other words, red, green, and blue micro OLED pixels do not have a luminance decay issue. Compared with that, each OLED pixels more or less suffers from a luminous decay, and the speed of decay varies. Like the transition of CCD to CMOS image sensors, also for the OLED devices and micro LEDs devices, displays the CMOS substrate is proved to be a very good cradle for enhanced system that includes not just LED, not just only the LED or OLED, but also the surrounding circuitry, A2Ds, logic, all those kinds of circuitry. So it's not just a switching matrix, but also embedded with we can embed now the chip with AI, with machine learning advanced algorithms. In this chart, you can see the size reductions of devices as we go up in the technology. You could see that we started from 1 millimeter, down to 200 micron, and now we even talk about pixels that are 2 micron wide. So OLED penetrate largely into the AR, VR technology over LED due to its superiority viewing angle, dark level, and fastest response time. But the main advantage of OLED over LED is for the handheld devices is of course the power consumption, even lower than active matrix OLED. The big challenge today in development of displays and GPUs for the virtual reality is to overcome what is known divergence accommodation conflicts. And this is when your brain receives mismatching cues between the distance of virtual 3D objects, which is divergence, and the focusing distance accommodation required for the eyes to focus on that object. Another challenge is the vestibular visual conflict, what we call the motion sickness. And the humans rely on multiple senses to perceive themselves motion in the real world. The response time is what makes the micro OLED the chosen display for VR and for example, we talk about the Facebook Oculus, and the source for further R&D towards overcoming the motion sickness and the divergence accommodation conflicts. So this is my summary slide. Industry 4 is driven by automotive and handheld devices, pushes the boundaries of semiconductors manufacturing on its demand for beyond state-of-the-art cyber-physical devices. While global shutter high-resolution industrial images are still in high demand, as we see in the 3D images with indirect time-of-flight and direct time-of-flight technologies are now at the heart of R&D, and this is it's mainly what I'm involved with right now. The micro LED is new, but far less mature than OLED, and it costs a lot more too. So even if it has had plenty of advantages, it's too soon to jump into conclusion that micro LED will supersede the OLED. Now, the increased demand for quality, zero waste, zero defect approach is mostly derived from the semiconductor technology advancement, increased demand for image sensor environmental approach, and capacity shortage, which I don't know if you are aware of this, but that's mostly what we have right now. So that was my presentation. And now I'm open for questions if you have.
Hello, Yoav. Thank you very much for a very insightful presentation on the project and on Tower's semi-role and capabilities. I believe we are almost out of time, but I think we have still a bit left to answer the question we received from audience. So basically, Yoav, what are the major benefits that the semiconductor industry can expect from the innovation delivered by the MADEin4 project?
Delivered by, sorry?
What major benefits can the semiconductor industry expect from the innovation delivered by the MADEin4 project?
The main advantage that we expect is to improve the metrology efficiency. I mean, we all need now because of we see all the shortage of the capabilities of manufacturing and all this kind of surge of demands for manufacturing. We must be more efficient. Must be more efficient. As I said, the price of quality is it becomes more and more important. So in the MADEin4, what we call the metrology, the next generation metrology, we expect to see some new algorithms, new systems that will make the design much more efficiency and with less issues during production.
Thank you very much, Yoav. And please, very quickly, when can we expect news on ULED from Tower?
Well, I believe that we mostly work now on the micro OLED with Aledia, with micro LED, but not with the OLED. With the OLED, we have some exciting developments that we are doing with in our fab in Japan. I think it will be shown more probably next year, starting to ramp into production, and perhaps maybe even in 2023. There will be some announcement and public announcement on that.
Fantastic, Yoav. Thank you very much for, again, a very good presentation, and also thank you to our audiences for attending the session, and please stay tuned for the upcoming session as well. Thank you very much, and I wish you all a good day.
Thank you.
Packaging has a unique role in the semiconductor industry. We're here to support the Moore's Law. We're also here to support the system integration. As the Moore's Law becomes more progressive, as the system level becomes more complex, the unique role of packaging also evolved along with time. The complexity of the functionality and also the unique requirement on cost and overall performance. Therefore, it is my view the packaging, we're working alone with the other members of the semiconductor industry. We will continue to prosper and make our unique contribution to the better of mankind.
It's time to unlock the future. From autonomous driving to renewable energy technology, tomorrow's communication networks, biometric sensing for our smart devices, and high-speed data processing. And Evotec's new cluster line generation is your partner, the flexible, industry-standard cluster line 200, delivering a complete portfolio of process technologies. Cluster line solutions can be configured just how you need them, from single process modules with manual load locks, perfect for R&D, to mass production platforms, combining different process technologies and semi-standard SMIF interfaces on a single tool, or unique Evotec solutions, offering combinations of single and batch module processing capability. It's time to open the door. Unlock your future today with the new cluster line.
Inspired by the human senses, Infineon developed sensors enabling smart devices to understand their surroundings and see, smell, feel, and hear. Smart Ear, extensive MEMS microphones. Smart Eye, 3D imagers. Smart Nose, extensive environmental sensors. Smart Eye, extensive radar sensors. Smart Feel, extensive pressure sensors. Infineon's extensive sensors, giving devices human senses. Part of your life, part of tomorrow. Infineon makes sense.
With chemistry, we can. JSR Corporation. At JSR, our business is supported by 3 business pillars: petrochemical products business, fine chemicals business, and life sciences business. The second is our fine chemicals business, which includes materials for semiconductors, displays, and edge computing. For semiconductors, we supply high-quality materials from plants in Japan, the United States, and Belgium. Among those materials is photoresist, which is essential for the higher resolution of semiconductors. We maintain a world-leading share in this segment by supplying the most advanced photoresists for nano-level patterns, which is 1/1,000,000th of a millimeter. We are supporting the evolution of semiconductors required for the Internet of Things and artificial intelligence. JSR will remain true to our corporate mission of we create value through materials to enrich society, people, and the environment.